Hey everyone, we're looking at section 10.4 today. We're going to talk about dividing radical expressions. So we just talked about multiplying radical expressions in 10.3, and I had kind of given you a little hint about what was going to happen in this section back when we were doing the 10.1, 10.2 notes, and we were looking at taking radicals of fractions. So let's just get started. I'll kind of go over this first example here. We have the cube root of 27 over 8. And that ends up being 3/2. So what times itself 3 times is 27 over 8. 3 times 3 times 3 is 27. 2 times 2 times 2 is 8. And so I had given you the little trick that you can split up the cube roots, and you end up cube root of 27 over cube root of 8 gives you the same answer. Well, in fact, that works all the time. Otherwise, I would have never told you that. And so here is the formal rule. And it says any nth root of a over b is the nth root of a divided by the nth root of b. Now, one of the things that you must keep is that the index must match on both radicals. So also remember, when you have an equal sign, you can read it from either direction. If you have two separate a numerator and a denominator, you can create a single fraction. You can go this way also and get a single fraction, the nth root of a over b. So it works in both directions. It doesn't matter. You can either split up or rejoin together. Okay, well, let's look at the first set of examples. So here we start with single fractions, and it says simplify by taking roots of the numerator and denominator. Assume all variables represent positive numbers. So let's switch colors here. We'll go blue. So the square root of 36 over y squared, remember, we can just split up, and you don't have to, but sometimes it allows you to simplify a little bit more than you could have before. So in this case, these are both perfect squares, so we end up with 6, and the square root of y squared, remember in section 10.3, we learned that we could divide the exponent by the index, and so we just end up pulling out y. So we get 6 over y. For number 2, when we split up the numerator separate from the denominator, we have the square root of 9y to the 9th over the square root of x to the 10th. Well, the square root of 9y to the 9th, we look at the coefficients separate from the exponents. So the square root of 9 is 3. Actually, and let's just do this. Let's break down, because y to the 9th is not a perfect square exponent. Remember, you're not taking the square root of 9. You're trying to divide 9 by the index, and 2 does not go evenly into 9. So you have to factor the y to the 9th as y to the 8th and y to the 1. And that way we can actually take out as many copies of y as possible. On the bottom, you do have a perfect square because 10 is divisible by the index, which is 2. So we end up at the final answer of 3, y to the 8th comes out as y to the 4th, but we're still left with the square root of y inside, and then the square root of x to the 10th is x to the 5th, and that's our final answer. For number 3, we're looking at the 4th root now, so we have the 4th root of p to the 13, q to the 4, all over the 4th root of r to the 8. Well, 4 does not go evenly into 13, so we're going to have to factor that p to the 13. And so we'll factor in what's the largest multiple of 4 inside of 13. It's 12. So we're going to factor as p to the 12 times p to the 1, where p to the 12 is the perfect 4th root, or power. And then q to the 4th is already a perfect 4th power. All over r to the 8, the 4th root of r to the 8, because r to the 8 is a perfect 4th power. All of those are multiples of 4. So pull out everything you can. P to the 12 comes out as p cubed. Q to the 4th comes out as q. You're still left with the 4th root of p all over the 4th root of r to the 8th, which is r squared. And there you go. So that's what we do when we split up. Now let's look at working in reverse and bringing the two back together. So example, divide and if possible simplify. So if you look at this, you see the square root of 33a, let's start with number 1, square root of 33a divided by the square root of 11a. So individually those cannot be simplified. There's nothing we can do there. So what we could try to do is at least create one single radical. And let me draw this a little bit taller. And so we say, well, that's the same as 33a over 11a. You can create one single square root. Well, that simplifies because 11 goes into 33 3 times and the a's cancel. And so you end up with just the square root of 3, which is a little bit nicer looking. So if we can do nothing, separately. Try merging the numerator and denominator and see if you can move, at least simplify or cancel something. All right, number 2, switch colors here. So number 2, so we can do a little bit on top, but we can do nothing on bottom. So let's merge them together and see if we can simplify anything first and then go through and simplify the rest. So we have 4th root, don't forget that index on the outside, a to the 9th, b to the 5th, all over 3b. Well, we can simplify this a little bit. 3 goes into 18 6 times, and then we have b cancels with that b to the 5th and leaves b to the 4th. So for this one, we end up having no denominator anymore, and we just end up with the 4th root of 6, a to the 9th, b to the 4th. And so then you say, well, can you simplify that anymore? And the answer is yeah, and you know because your exponents are not less than your index. So we need to factor this guy. The 6 I can't do much with. There's not a perfect 4th power inside of 6. But the a to the 9th I can factor as a to the 8th and a to the 1. And b to the 4th is a perfect 4th power, so I leave him alone. Pull out what you can. A to the 8th, divide by the index, comes out as a squared. B to the 4th comes out as b. And you're left with the 4th root of 6a. All right, and our last guy, so this is where I would say, hey, you give this one a try. Grab that color. So again, not much we can do on the bottom. Let's try merging and see if anything cancels. So we have this 2 on the outside. Now there's a couple ways to deal with that. It's really a 1/2 because when you're dividing by 2, you can just rewrite him as a coefficient. And then you have this 72xy over 2. So this 2 went here. This 2 went under the radical. Well, this 2 and this 72 cancel to give you 36. So you end up with 1/2 times, there's no more denominator, so you just have the numerator there, 36xy. Well, can you simplify that? Sure you can. 36 is a perfect square. X and y, you can't pull out any variables there. So we have the 1/2 in front. 36 comes out, but you've already got the 1/2, so what do? 36 is going to come out as a 6. Well, you multiply. So that's 1/2 times 6 times the square root of xy. Well, what's 1/2 of 6? 3. So you end up with 3 square roots of xy. So that's one way to handle it. Another way you could handle it is you could simplify the 72 to begin with. So I'll say, let's go version 1 here, and then version 2. And of course, it doesn't matter to me. I just want to give you a couple of options with a problem like this. So you could, I'm going to start with the original problem, 72, square root of 72xy over 2 root 2. You could simplify that numerator to begin with. That 72 has a perfect square in it, 36. So this is 36 times 2 times x times y. And on bottom, you just have the 2 root 2. Well, the 36 comes out and you end up with 6 square roots of 2xy over 2 root 2. The 2 and the 6 cancel, leave behind a 3. And then you can now join up these two radicals. So we end up with 3 times the square root of 2xy over 2. 2's cancel, and we end up with 3 square roots of xy. So either way we get there, there's some algebra involved, and you really have to know your rules. One of the big takeaways is that if you pull something out of a radical and there's already a number right there, you just multiply whatever comes out of that radical. Okay, So the next thing we're going to talk about is rationalizing, and that comes into play with fractions, which is what we're studying in this section. And you may notice we never really end up with a radical in a denominator if you look at all of our answers. And that's pretty standard fare. Typically, radicals are not allowed in final answers in the denominator. Every once in a while, they'll go after the numerator and they'll want you to make sure there's no radical in the numerator, but 90% of the time, the rule is no radical in the denominator, and that is called rationalizing when you get rid of a radical. So let's look at this second page here. So rationalizing denominators or numerators with one term. We'll talk about two terms later on. The expressions 1 over the square root of 2 and square root of 2 over 2 are equivalent. If you put them in your calculator, you get the same decimal number. There are instances in mathematics where it is preferable to eliminate the radical from the numerator or the denominator. This is called rationalizing. So the big reason we usually don't want a radical in the denominator is because when you're combining fractions, you need a common denominator, and that becomes a much more tedious process when you've got a radical in the denominator. Where if you just have nice whole numbers, then it's a lot easier to find a common denominator. So how do I rationalize? Well, I'm going to show you first, and then I'll explain to you why. The only thing I can really do to simplify when I don't have an equation with a fraction is multiply top and bottom. So I'm going to multiply top and bottom by the square root of 2, and that's going to seem kind of magical. Why did I pick the square root of 2? Well, watch what happens when I do this. I'm going to multiply straight across the top. 1 times the square root of 2 in the numerator is just square root of 2. On bottom, I end up with the square root of 4. Remember from section 10.3, if you multiply where both factors are under the radical, you can multiply those two radicals and get the same answer. Well, what's the square root of 4 now? That's just 2. So we end up with square root of 2 over 2. So why did I pick to multiply top and bottom by the square root of 2? Because I matched what was down here. And the reason I did that is I knew I would create a perfect square that I could take the square root of. Now for our purposes, I'm going to stick with square roots because that's typically when you're rationalizing. It's typically square roots that you rationalize, but you can use methods for cube roots, fourth roots, so on and so forth. Let's look at number 2. So now that I've kind of given you the trick to this, let's look at number 2. Square root of 1/7. So a big good first step is to separate the square root, separate the fraction. So this is the square root of 1 over the square root of 7. Well, the square root of 1 is just 1, so this is 1 over the square root of 7. They want you to rationalize the denominator, which means get rid of the radical in the denominator. And so in order to do that, I'm going to multiply, and I'll write it here now, multiply top and bottom by the radical in the denominator. All right, so that means I'm going to multiply, and I'll come up with let's grab a different color here so you can see that. I'm going to multiply top and bottom by the square root of 7. So when I do that, I end up with square root of 7 on top, 1 times the square root of 7, over 7. Now notice I can't cancel those 7s because the numerator is really not a 7. It's a square root of 7, which is a number much smaller than 7. So you end up with square root of 7 over 7. And in fact, we know the square root of 7 is somewhere between 2 and 3. How do we know that? Well, because the square root of 4 is 2 and the square root of 9 is 3. And 7 is between those two numbers. And so we could approximate and say we know the numerator is somewhere between 2 and 3, denominator 7. You can never cancel something in a radical with something not in a radical, or something inside the radical with something outside a radical. All right, now number 3 becomes a little more tricky. So a lot of students with number 3, they'll just multiply top and bottom by the square root of 12y. I recommend against that. And the reason is because the square root of 12 can be simplified. So what I would do is I would simplify everything in the radical first and then multiply top and bottom by whatever you have to multiply by. So 12 has a hidden 4 inside of it. So I would pull that 4 out of the radical first, and I would get 2 times the square root of 3y. Then multiply top and bottom, and I'll come back in and use that different color, by the square root of 3y, not the square root of 12y. And you're wondering why. Get it? Why? Because students multiply top and bottom by that bigger number, and then they forget to reduce it at the end. Where if you make a rule for yourself, just reduce all radicals when you start, you're much more likely to get the final answer correct. So I've just found it to be more effective for students to actually remember to reduce that 12 at some point. So on top, I just get 7 square roots of 3y. What do you get on bottom? Well, 2 times, and then you get square root of 3y, square root of 3y. Well, that gives me the square root of 9y squared, which is just 3y. So you really get 2 times 3y. Notice I put parentheses because this is multiplication. So we get 7 square roots of 3y over 6y. Now, one thing you may notice is when we match the radicals, the square roots, you always just get whatever's inside. Look here and then look here. It's always how it simplifies. We multiply 2 square roots of 7, we just get 7. Move up a little bit. We multiply 2 square roots of 2, and you end up with just 2. So in fact, I'll just say notice, if you get the square root of x times the square root of x, you just get x. Square root of 7 times the square root of 7 is just 7, square root of 49. And then if you get, let's say, square root of star times square root of star, guess what you're going to get? Star. It doesn't matter what's inside. You're just going to get whatever's inside because you're squaring a square root basically, and those are opposites of each other. They're what we call inverses. So you have a square root, you have 2 square roots, and you're squaring that, so you're undoing the square root essentially, and you just get whatever's inside. So that will make a little bit quicker work if you notice that pattern. All right, now this second set, I wanted to do a couple of examples like this because they switched it up on you. Rationalize each numerator. So when you're doing your homework and taking your test, make sure to pay attention to the directions and what they want you to rationalize. We get sort of in a pattern of always rationalizing the denominator, and every once in a while there's a good reason to rationalize a numerator, so we want to practice that too. All right, so example number 1, they want us to rationalize the numerator. Now remember, I told you that I'm going to pull out any perfect square factors first, and there is a hidden 4 inside of this 8. So I'm going to break that down first. I'm going to break down anything I can. So square root of 8 is 2 square roots of 2. That's one we see a lot. Here you can do some canceling if you want. The 2's eventually are going to cancel. So they're both outside, so we can cancel. And then I'm going to multiply top and bottom by the square root of 2. Now remember, because I'm matching the numerator, not the denominator this time. So square root of 2 times the square root of 2 on top is just 2. On bottom, the square root of 3x times the square root of 2 is the square root of 6x. And that is done. Number 2, I would say at this point, I want you to give this one a try. So pause the video, simplify the radical. You don't get the wrong answer if you multiply top and bottom by the original numerator. It's just one of those things, like I said, that you got to remember to simplify at some point, so you might as well do it at the beginning. All right, so for number 2, I'm going to switch up colors here. The first thing I'm going to do is I'm going to split up the fraction. And then I'm going to simplify any of these that I can, and there is a hidden variable of x that I can pull out. So I'm going to break down x into x squared and x to the first power, and then I have y to the first power. On bottom, I just still have the square root of 7. The x squared comes out, he comes out as x, and I'm left with the square root of xy over the square root of 7. So I would then multiply top and bottom by the square root of xy because I'm rationalizing the numerator, not the denominator. So on top, I end up with x times, what's the square root of xy times the square root of xy? It's just xy. And on bottom, we end up square root of 7 times the square root of xy is the square root of 7xy. On top, what's x times xy? So we did a little bit of review work on multiplying monomials, and we just end up with x squared y over the square root of 7xy. All right, let's look at the last contender here. So for this guy, we can simplify. I'm going to simplify any radical I can, like I said. So on top, I can't simplify. This is why I cross my z's. Otherwise, my 2's and my z's look exactly the same. I'll try and loop that too. And then on bottom, I can pull out the 4. So there's a factor of 4 inside of 20. So I end up with 4 square roots of 2z all over 2 square roots of 5. 2 goes into 4 2 times. So I end up with 2 square roots of 2z all over the square root of 5. Now I'm going to come in and multiply top and bottom by the square root of 2z because I'm rationalizing the numerator. So on top I end up with the 2 on the outside, and then square root of 2z square root of 2z is just 2z all over 5 times square root of 5 times the square root of 2z, which is the square root of 10z. On top we end up with 4z. On bottom we end up with the square root of 10z. You cannot cancel those z's. You cannot cancel that 4 and 10 because the z and the 10 are inside the radical. They're not really a 10 and a z. It's the square root of that. All right. So that is it for section 10.4. Go and give the homework a try now. And as always, ask questions if necessary. And I will see you in section 10.5 to be continued.